Dear students, today we'll see Unit 2, Basics of Semiconductor Devices, in which we'll see Section 9 of this lab, in which we are going to see PN junction diode, formation of PN junction, potential barrier, depletion region, forward and reverse biasing of diode, VI or characteristics of diode, diode ratings and parameters. So let's start with the topic PN junction diode. And in this, we are going to see this following contains. Number one is formation of PN junction diode, how a PN junction is formed from P-type and N-type material. Then what is potential barrier, what is depletion region, these both things in PN junction. Then a PN junction taken as a diode, forward and reverse biasing of diode. Then fifth, VI characteristics, that is voltage, current characteristics of diode. And then sixth, diode ratings and parameters. So let's start with the formation of PN junction. And for that, we will see what is P type of material and what is N type of material. So in our last session, we have studied what is an atomic structure, what was a semiconductor, what was a pure semiconductor, which was called as intrinsic semiconductor. And when you add impurity to the pure semiconductor, you can get extrinsic semiconductor, which can be of two types, P-type and N-type. So here in P-type, we can see the majority charge carriers are holes as shown here. These are majority charge carriers. They are more in number, so they are called as majority charge carriers. And they are the one which are constituting the flow of current. Okay. And we have very few number of free electrons which form because of temperature, some covalence bond break, and we have a very few number of free electrons which can make your minority charge carriers. So in P-type, holes are majority charge carriers, and free electrons are minority charge carriers. So they are less in numbers. These holes you're going to get because of doping, and these free electrons you're going to get because of the temperature which naturally forms. Okay. Now same type in N type, if you see, it is the other way around. In N type, because you're adding the pentavalent impurity, you're getting a lot number of free electrons. So free electrons which are here are majority free electrons. Okay. And there are few holes which are formed because of temperature, covalent bond breaking, and those will be called as minority holes. Okay, minority charge carriers as holes, So as a conclusion, we can say that now P-type semiconductor is a material in which holes are many in number, so they are majority charge carriers, and electrons are few, free electrons are few, so they are minority charge carriers. And in N-type semiconductor, free electrons are many, so they are majority charge carriers, and holes are few, they are called as minority charge carriers. Then the same theory is given here, P-type and N-type semiconductor. The P-type semiconductor is formed by adding trivalent impurity to the pure or intrinsic semiconductor, while N-type semiconductor is formed by adding pentavalent impurity to the pure or intrinsic semiconductor. In P-type semiconductor, holes are the majority charge carriers, while free electrons are the minority charge carriers. On the other hand, in N-type semiconductor, free electrons are the majority charge carriers, while holes are the minority charge carriers. This is the theory before we join P and N and make a PN junction. So now we have seen what is P-type semiconductor and N-type semiconductor. Okay. Then we'll go to see what happens when we join a P and N type of semiconductor. So here you can see P-type semiconductor. So this is your P-type semiconductor shown. This is P-type semiconductor. And here you can see N-type semiconductor. This is N-type semiconductor. Okay, so P and N, when they are joined, the interfacing boundary, this boundary is called as PN junction. So when P and N type of semiconductor are joined together, the interfacing boundary, the junction between them is known as PN junction. So here if you see the basic definition of PN junction, if p-type semiconductor is joined with n-type semiconductor, a PN junction is formed. The region in which the p and n-type semiconductors are joined is called as PN junction. Then we'll go to see what happens when a p and n junction is joined. Okay, so when p and n junction are joined, so initially what will happen is electrons from n-type will be attracted towards the holes of p-type, and the holes from p-type will be attracted towards the electrons of n-type. Okay, now this crossover goes on. The majority charge carrier electrons which are there in n-type start crossing towards the p-type from the junction, and the majority charge carriers which are holes in p-type will start crossing towards n-type because of their different attractive charges. Okay, now here when the electron moves from n-type and goes to p-type, there is an absent place of electron, and that absent place becomes a immobile carrier, immobile charge. Okay, so immobile charge, it is not going to move, and that becomes a positive ion. So positive ion we have shown here. Okay, similarly, when a hole goes to the n-type region, the absent place of hole is taken as a negative ion. Okay, negative ion, and that is also immobile. This can be explained in other way also. Whenever the free electrons from n-type go towards holes of p-type and get combined with them, okay, that becomes a negative ion. And because the electrons have moved away from n-type, that absent place of electron is taken as positive ion. So at any theory, if you go, you are going to see that whenever this movement of electrons to p-type and holes to n-type takes place, there will be ions which will be produced. The absent place of electron will be taken as positive ions. Here in n-type semiconductors we have shown, and the absent place of hole, or when the electron come and gets combined with the hole, that can be taken as a negative ion here. So negative ion, and this positive ion and negative ion are not carriers, charge carriers which can carry current. They are not movable, so they are immobile, they are not moving, they are fixed at. Okay, and they mostly concentrate near the junction. They mostly concentrate near the junction of the PN junction. So here we can see the theory for the same. The free electrons that are crossing the junction from n side provide extra electrons to the atom on the p side by filling holes in the p side atoms. The atom that gains extra electron at p has more number of electrons than protons. We know that when the atom gains an extra electron from the outside atom, it will become a negative ion. Thus, here you can see the conclusion. Each free electron that is crossing the junction from n side to fill the hole in the p side atom creates a negative ion at p side. Similarly, each free electron that left the parent atom at n side to fill the hole in p side atom creates a positive ion at n side. Okay, so this is how the ions are formed. Now, this formation of ion, what it is doing? So we are having again the same image here. So you are having a p-type semiconductor which is connected to, which is joined to n-type semiconductor, and then electrons are here, holes are here, and in between you can see the formation of ions because the electrons from here were moving and have stopped moving now, and holes from here were moving and have stopped moving. That crossover has stopped, and these ions are formed here near the junction. Now this formation of this positive and negative ions near the junction says that you are having immobile charges near the junction. They are not going to move. They are not going to move. And here in this area, you don't find any majority charge carriers of the p-type semiconductor or n-type semiconductor. So here the majority charge carriers have vanished. They have become very, very less, or they are zero. So this area is depleted from the majority charge carriers. So because of that, this area is called as depletion region. So here you can see this is your depletion region. From here to here is called as depletion region. Okay. So we'll see the definition for that. Depletion region. Thus, immobile, which are not moving, positive charge at N side and immobile negative charge at P side near the junction acts like a barrier, acts like an obstruction, acts like a barrier or wall, and prevent the further flow of electrons and holes. So because it forms, there is no further movement of free electrons from N to P side and holes from P to N side. The region near the junction where flow of charge carriers are decreased over a given time and finally results in empty charge carriers or full of immobile charge carriers. In that area, there are no moving charge carriers. Okay, that area which is depleted of moving charge carriers is called as depletion region. Then in the same depletion region, if you see that region where the depleted area is there, you can see this positive ion. So this can be taken as a positive charge here, and this is negative ion. This can be taken as a negative charge, and this will have its own electric field, and it will have its own voltage, which is called as potential, and that voltage is going to oppose the main current flow of the PN junction or diode, and because it is opposing, it is called as barrier potential or potential barrier. So here this potential barrier, this voltage will be 0.3 volt for germanium diode and 0.7 volt for silicon diode. Now we are going to call PN junction as diode because this arrangement is a diode arrangement. Clear? Now this is called as barrier potential because whenever you want the diode to conduct, whenever you want a diode to have a flow of current through it, it has to first overcome, the applied voltage has to first overcome this voltage, which is barrier, which is opposing it. And after it overcomes this, then if you increase the voltage, the current will be flowing more in the diode. Okay. So here we'll see what is potential barrier. The electric field formed in the depletion region acts as a barrier. External energy must be applied to get the electrons to move across the barrier of the electric field. The potential difference required to move the electrons through the electric field is called the potential barrier. A potential barrier of a PN junction depends on the type of semiconductor material, amount of doping, and temperature. This is approximately 0.7 volt for silicon and 0.3 volt for germanium. Then we can see what are the forward bias and reverse biases of a PN junction diode. Okay, so here we have shown what is forward bias. So when do you say PN junction is forward bias or a diode is forward bias? When you connect a battery and the positive terminal of the battery, if it is connected to the p-type semiconductor of the PN junction or a diode, and negative terminal of the battery is connected to the n-type semiconductor of PN junction or diode, then this arrangement is called as forward biasing. You are biasing the diode in a forward way. Okay. Now because of this, what will happen is, because you are connecting plus positive potential to the p-type, these holes which are assumed as positive charge particles will start moving like this. It will give a force for them to move like this to cross the junction. And similarly here, because you're having negative charge, negative part of the battery, negative potential of the battery connected to the negative charge particles electrons, that will also repel them, and they also have a flow in this direction. So they are there now to cross the junction. Okay. Now this is where your junction also is narrow in this case. And if you increase the voltage of the battery little more, this voltage, which was potential barrier, which was opposing this main battery voltage will be overcome, and then these charge carriers can move across the junction, and we can say the diode is conducting. So this is your forward bias. And if you go to see a reverse bias connection, then reverse bias connection will be just opposite to forward bias. In a reverse bias, the negative terminal of the battery is connected to the p-type region of the PN junction or diode, and positive terminal of the battery is connected to the n-type region or junction, ion type of a PN junction or diode. Now, because of this, what will happen is these holes which are assumed to be positive charged will be attracted towards this negative of the battery, and these electrons which are negative charge will be attracted towards this positive terminal of the battery, and the region, the depletion region between at the junction, okay, between the P and N material will increase in width. This width will increase because the majority charge carriers are moving in opposite directions and they are going out towards the battery terminal. Okay. So in this case, your depletion region will be wide in a reverse biasing condition. Then how does the characteristics in forward bias look like? Now, if your PN junction or diode is a silicon diode, then you can see the forward characteristics will start from zero. The x-axis is taken as the forward voltage here, and the y-axis is taken as the forward current here. So initially, when you increase the voltage from zero, okay, it will not show any flow of current till you reaches till you reach approximately 0.7 volt in case of silicon, and then you can see there is a rise in the current. Okay, so you have to overcome that 0.7 volt, which is the potential barrier. You have to overcome the applied voltage should be more than 0.7 volt, and then only you will see a current flowing in the diode. Similarly, if you have a germanium type of diode, then that uh, potential barrier will be little less here. So it is 0.3 volt. So here again, you can start from zero. You can increase the voltage as the voltage reaches 0.3 and overcomes the potential barrier is overcome. Then you can see current is flowing more in the diode. Okay, so this is the forward characteristics of germanium diode. Similarly, if you go to see reverse characteristics, so in reverse characteristics, the reverse connection of the battery will act as forward bias to the minority charge carriers. Now here the concept of minority charge carriers becomes important. Now initially when you apply the reverse voltage, there will be a very few minority charge carriers, okay? But as you reach a certain breakdown voltage, you can see the minority charge carrier will multiple and increase in number, and there will be a heavy reverse current flowing because of minority charge carriers, not because of majority charge carriers, because of minority charge carriers. This will be your reverse breakdown. Then if you see both the characteristics together, so this will be your voltage current characteristics of PN junction or diode, voltage current characteristics of diode or PN junction, you can call it. So here you can see the x-axis is your voltage and y-axis is current, and this is your 0 point. So here you can see the forward biasing. This is forward biasing. As you increase the voltage and once the potential barrier is crossed, the current will go on increasing. And in reverse bias, till you reach the reverse voltage, a small leakage current flows. After that, minority charge carriers will increase and there will be a lot of heavy reverse current flowing. Then we'll see what are the diode ratings and parameters. Initially, we'll see some important terms and then we'll go to see what are the ratings and parameters in detail. So the important terms of your ratings and parameters of diode. The first one is the breakdown voltage. It is the minimum. It is the minimum reverse bias voltage at which PN junction breaks down with sudden rise in reverse current. So this is what we have seen in the reverse characteristics. Then second one is knee voltage, what we see in the forward characteristics. It is the forward voltage at which the current through the junction starts to increase rapidly. Okay, so here if you go back and see the VI characteristics, so here in the forward region, okay, in the forward region, when this thing happens, once you overcome the potential barrier, okay, now this will give you the knee type opposition, and this will be called as your knee voltage here. This will be called as your knee voltage, whatever you get here. And that will, after that, once you cross the knee voltage, the current will increase. Okay. Then we'll go to the third one, peak inverse voltage. It is the maximum reverse voltage that can be applied to the PN junction without damaging it. Then fourth one, maximum forward rating. It is the highest instantaneous forward current that a PN junction can pass without damaging it. Then fifth one, maximum power rating. It is the maximum power that can be dissipated from the junction without damaging the junction. Then we'll see few of these terms, few of these ratings in detail. Forward voltage drop, VF. The voltage drop measured across forward bias diode during conduction is known as forward voltage drop. A silicon diode has a forward voltage drop of 0.6 volt, and a germanium diode has a forward voltage drop of 0.7 volt. Then peak inverse voltage. Peak inverse voltage refers to the maximum reverse bias voltage this we have seen, which withstands without damaging itself before breakdown. The peak inverse voltage is also known as peak reverse voltage. The peak inverse voltage rating of a diode increases and decreases with temperature. A typical diode used in rectifiers has a peak inverse voltage rating of at least 50 volt DC at room temperature. Then forward voltage VF. A certain amount of voltage is required to trigger a conduction, that is flow of current in the forward direction. Forward voltage can be defined as the minimum voltage that when applied across the diode triggers conduction in the diode that will make the current to flow through the diode. For silicon diode, the typical forward voltage is 0.7 volt, and for germanium diode, the typical forward voltage is 0.3 volt. This is where your potential barrier is overcome and the current starts flowing in the diode. Then what is maximum reverse current or leakage current? The maximum amount of current the diode can conduct during reverse bias is known as reverse leakage current or leakage current. It is negligible when compared to the forward or continuous current. For an ideal diode, the leakage current is assumed to be zero. Initially, it will be zero till you reach the reverse breakdown voltage. After you reach the reverse breakdown voltage, then the minority charge carriers will start multiplying, and there will be a heavy inrush of minority charge carrier, which will give a heavy breakdown reverse current. Then what is maximum power dissipation? PD max. Maximum power dissipation is the maximum possible power dissipation in the diode when operating in forward bias. It is typically the multiplication of forward voltage by the forward continuous current. The PN junction offers a resistance to the current flow resulting in power loss in the form of heat across the junction. Then what is reverse recovery time, TRR? The amount of time a diode takes to stop conduction. This is very important in switching applications. The amount of time a diode takes to stop conducting current as the voltage across it alternates or changes from forward bias to reverse bias. The amount of time a diode takes to stop conduction as the voltage across it alternates from forward bias to reverse bias is known as reverse recovery time. Theoretically, the diode must block the current flow instantaneously. The reverse recovery time of the diode is rated in nanoseconds. Thank you, students.